Okay, now what we said is we're going to make a cut here and separate these guys into two parts. And so whenever I do that, what I'm going to end up with is a free body diagram of block A or crate A. And on that free body diagram, I have 392.4 newtons headed downward. The tension in that cable, I'm just going to call T. And then I've already committed to the fact that this is NA. And this guy here, because we're assuming that we're impending motion, it'll be 0.25 times NA. And if I draw the other one, then using Newton's third law, this reaction and this reaction will have to be equal in magnitude but opposite in direction. So this tension, this magnitude will be the same over here, and I'll have 392.4 newtons headed down, and I'll have the normal force at B, and then I'll have the friction force, which will be 0.25 times the normal force. And then we said that you had this force here, which was P, but if we wanted to break that into its components, which makes it a little easier for us to think about, we know that angle is 30 degrees, so that component then becomes 0.866 times P, and that component becomes 0.5 times P. Okay, and we can use those components as opposed to using that force. Now, if I look at this, I have two unknowns. Let me just list them. The normal at A and the tension. Now, when I move over here, the tension is over there, but it's not a new unknown, so it's just there. Then I have the normal at B, and then I have the value P. So if I look at it like that, I have four unknowns. Now, you see, a minute ago, I'm looking at this, and the tension force didn't come into play, because if you're looking at this total thing as a system, that tension force becomes an internal force, and it's not there. But when you make this cut and you separate these guys into two separate blocks, that exposes the tension. So I've got the normal at A, and I've got the tension, and I've got the normal at B, and the tension, and the magnitude of P. So I've got four unknowns. So that means I picked up an extra unknown, because over here I said I started out with 3, and now I'm telling you I have 4. But you see, the difference is that over here for crate A, I can sum forces in the X direction, and I can sum forces in the Y direction. So that's 2 equations. And then over here for crate B, I can sum forces in the X direction, and I can sum forces in the Y direction. And so if I look at that, I've got 1, 2, 3, 4 equations, and I've got 4 unknowns. So if I take these crates one at a time, that should be my best bet for getting to the answer. Now, at that point, the question becomes, should I start with this crate or should I start with this crate? Well, the truth is it doesn't matter, because if I start with this crate, I'll have valid equations. If I start with this crate, I'll have valid equations. The difference is that if I start with this crate by itself has 2 unknowns and I have 2 equations, so I'll be able to directly solve for these things. If I start with this crate, I've got 1, 2, 3 unknowns, but only 2 equations, and so what I'll be left with there is equations that are useful equations, but they would then have to be combined with the equations from this one in order to get the solution. So it makes sense to start here. Now, every time we work a problem like this, you're going to arrive at a different conclusion as to what makes sense with regard to starting. This problem, it makes sense to start here. Another problem, it may not be that way. Then there are other problems where you're at a deficit no matter where you start, so you just have to start writing equations and do the best you can. But we're going to start here because that seems to make sense.